Good morning, everyone. Today I'm going to present our work, AWARE, which is to automate workload autoscaling with reinforcement learning in production cloud systems. And this work is in collaboration with IBM Research. So cloud systems is a natural arena for reinforcement learning, or RL, and this is because of several reasons. First, cloud systems management tasks are full of sequential decision-making processes. And examples include resource management, which is everywhere in the computer systems across different layers in the hierarchy. And other examples include job scheduling, congestion control, etc. And these problems are usually well-defined, and they have been here, been around for a long time, but yet remain significantly challenging to solve. And the main reason is that these problems are usually hard to model, and existing approaches mostly rely on human-engineered heuristics or static policies. IO represents a popular category of an online learning-based approach. It enables us to use deep neural networks, or DNNs, to represent or express those complex dynamics with raw and noisy signals, and they can also be used to represent policies without any inaccurate assumption about the system, for example, using a system model. And to train these deep neural networks, they can be data hungry. But fortunately, we have abundant data generated in modern cloud systems, which could be monitoring measurements, real-time system metrics, or time series performance metrics, etc. And examples include, for example, in Kubernetes or OpenShift, we have Prometheus. And in production data centers, we also have production systems like Monarch from Google or Scuba system from Meta. And actually, there have been a large body of work from academia modeling reinforcement, system management tasks in reinforcement learning. And they train an IR agent in each task to learn the optimal policy. And then they show that the IR-based controller can outperform the baseline in each system task. Examples include cluster management, scheduling, networking, database optimization, and also cloud resource management autoscaling. And in this work, I'm going to focus on workload autoscaling as a concrete example of cloud resource management. So to start with, as a primer in RL, the system task is modeled as a Markov decision process. And an artificial agent is created to interact with that environment in a step-by-step fashion. At each time step t, it's going to take an observation or state from the environment, st, and make an action, AT, and receive rewards, RT, which represent how good this action is given the current context or given the current state of the environment. And this IR agent is designed and to continue to optimize for specific workloads experienced in the cloud system. For example, it could be small jobs, low load, periodicity, etc. And the IR agent will continually to learn and maximize the expected cumulative reward within any trajectory, in T steps. And the life cycle of the IR agent basically consists of two parts, policy training and policy serving. In policy training, the model parameters are updated based on the reward it gets, and then basically perform gradient descent. And after the convergence, it's going to be in the policy serving stage, and the trained model will be used to do inference. And at this period of time, the model parameters are no longer being updated. And the direct benefit of IO is we can align the objectives with reward functions, and basically to guide the training and indicate how good the performance of the agent is. And for example, in cloud system management, we can use it to align with the target of SLOs of the applications or systems, or to achieve higher cluster utilization. However, when porting the IO to production, there's a few gaps. First, it's there's a gap to bridge IO model advances and the development to production, and there's a framework needed to allow robust and reliable deployment of IO-based controllers in real production systems. So in order to deliver such a framework, when we want to manage and run the IO-based controller in production cloud systems, let's look at the example of multi-dimensional workload autoscaling in Kubernetes. In a Kubernetes cluster, the workloads are deployed as pods and containers in the cluster, and then the IO agent, in order to meet the application SLOs or achieve higher level of utilization of the resources, is going to control the vertical scaling, which is to resize the container in CPU or memory, and also horizontal scaling, which is to adjust the number of replicas. And this resource scheduling problem is in general NP hard, and the optimal decision is usually based on like the workload. It's workload dependent, which means IO is pretty suitable for this kind of learning the like optimal policy and adapt to the dynamic cloud environment. However, like we have identified 3 main challenges when putting IO-based solutions in production, and to enable built-in intelligence with less manual intervention while achieving high robustness and self-adaptation in both IO training and policy serving. First, in the early stages of the IO training, and because of the IO exploration, the agent tends to generate like worse than baseline, like those poor auto-scaling decisions. And in our experiment, we found that because of over-provisioning, the CPU utilization and memory utilization deficit can be up to 42% and 30%. And there are also SLO violations because of the policy is unable to rescale the resources properly for any workload changes. And in our solution, we propose to have reliable IO exploration with like offline training together with, combined with online training and inference, and we call it bootstrapping. The benefit of doing this bootstrapping is to have significantly higher reward indicated in this blue shaded area compared to the baseline, which is our agent firm in red. And secondly, during like online serving, policy serving stage, our agent performance degrades when workloads are updated. For example, it could be like a file size changes or table size changes, or it could be like an update in ML models, image dimensions. And in our experiment, we found that this kind of workload changes can lead to up to 21.8% reward drops during online policy serving stage. And in our solution, we propose to insert continuous monitoring and retraining detection and trigger mechanism in the online policy serving stage. And last but not least, there's also a challenge when we want to adapt the policy to new workloads, especially for those workloads or applications that are unseen in the training dataset. And we found that when doing that adaptation, there could be 45% reward drops, which basically means that we need to retrain the model or agent for more than 200 episodes. And in our solution, which I will talk about it like later, we're gonna tackle this challenge using meta-learning. So how does Aware look like? Basically combining these solutions for each of the challenges, Aware consists of 4 key components. First, we have an MPA, multi-dimensional pod autoscaler system for IO training. Basically, it constructs the IO environment by wrapping up the metric collection and also the scaling action actuation. And second, we have the IO bootstrapper module. And the bootstrapper module basically combines the offline training together with online training. In the online training stage, the IO agent will directly interact with the IO API gateway, like with the IO environment through this API gateway. And then in the offline training mode, the IO bootstrapper will intercept the interaction with the IO environment by taking the actions from the non-IO based autoscaler, for example, vertical autoscaling by VPA and horizontal autoscaling by HPA. And then the IO agent will train in the offline fashion. So basically, the IO API gateway will store the trajectories of the state action reward at each time step into an IO trajectory database. And the IO agent will treat this database as a replay buffer to draw trajectories from this database, and then train the model, update model parameters in an offline fashion. And third, we have an IO retraining detection and the trigger module. By like continuously observing the recent rewards from the IO trajectory database, and then switching between the policy serving stage and policy training stage whenever necessary by comparing to the threshold specified by the user. And lastly, we have a meta-learning module. The key idea here is to model the IO agent as a base learner, and then we create a meta-learner so that we can learn to generate an embedding that can be used to precisely differentiate and represent each individual environment. So let's look at each component in more detail. First, in MPA, so multi-dimensional pod autoscaler is basically like an open source framework, and it allows general workloads on Kubernetes to use IO-based autoscalers such as firm. And it also enables us to reuse HPA and VPA as a fallback to IO to have a default autoscaling algorithm. So for any application deployment in Kubernetes, the HPA controller is going to pull the metrics from the metrics server and then adjust the horizontal, like the number of replicas based on like a threshold. It's either based on the utilization or application metrics. For example, it could be CPU utilization. And then the VPA like operator is going to have a custom resource definition first, indicating the auto-scaling status and the specs. And then it creates 3 controllers. The VPA recommender will set the configuration of the vertical auto-scaling based on historical metrics. And then the VPA updater and automation controller will watch for this like VPA CR change and then resize the pods whenever necessary. MPA follows the similar style as the VPA, and we want to separate the scaling recommendation from the actuation. And in this way, we can support customized plug-and-play multidimensional auto-scaling algorithm so that we can use it to train our algorithm. And then let's look at this in detail. So basically, we have the application deployment in the Kubernetes cluster. And then we also have the metric server. The recommender is going to get the measurements from the metric server API and gets the recommendation from either the IO controller or is from the non-IO-based controller, VP and HPA by default. And after getting that recommendation, this recommender will set the auto-scaling configurations in the MPA API. Then we have the updater to watch for any changes in the horizontal configurations, and automation controller to watch for the vertical configuration updates. And then they're going to actuate this auto-scaling like for horizontal auto-scaling and vertical auto-scaling. So MPA module enables step-by-step interaction with the environment for IO training. And then let's look at how IO bootstrapping combines offline and online training. So after initialized, the IO agent will enter offline training stage first by default, unless the user skips it explicitly. In the offline training mode, the VP and HP autoscalers will be used to interact with the API, set the scaling configurations at the runtime, and then meanwhile, the IO agent is trained in an offline fashion, drawing trajectories from the replay buffer, which is the database, and then update the model parameters. So when we found that the reward when we evaluate the IO agent in any trajectory is larger than a threshold specified by the user, it's going to enter the online mode. In the online mode, the IO agent will directly interact with the MPA environment, which is the IO environment. And after we go to the online mode, in policy serving and policy training, we basically observe the recent reward by the agent continuously, and then compare to the threshold for the average and the standard deviation. If the reward fluctuates a lot, or the average reward is lower than a user specified threshold, which indicates a non-convergence, and then the model training will continue, will stay in the policy training stage, and then the model or policy will continue to be updated. And otherwise, we're gonna stay in the policy serving stage. And lastly, we address the model adaptation challenge with meta-learning. The goal is to reduce our model training time and then adapt quickly to new application workloads, which can be unseen during training. So how does this achieve this? Our key idea is, as I mentioned, to model each agent as a base learner, and then create a meta-learner to learn to generate an embedding that can accurately represent each environment. The embedding will be fed back to the base learner as the state input. And basically, the learned policy is like customized to the environment. And this policy or policy network in IO is conditioned on this embedding. And why do we want to use meta-learning? Meta-learning is known as like learning to learn. It's capable of adapting well or generalizing to new environments that have never been encountered during training. And this adaptation process requires only like minimal exposure to the environment, which is only like just enough for generating the embeddings. And in our case, it's 32 trajectories, for example. And meta-learning provides a systematic framework that enables automatically adjusting the internal hidden states in the policy network of IL. And after combining with IL, it means that the learned policy is conditioned on the application. So let's look at the architecture. As I mentioned, that IO agent is like a base learner here, which takes the states on the left-hand side and then generate the scaling actions. Then we create a meta learner. The IO trajectories from like interacting with each environment I, which represent the application workloads in the environment, are collected then. And these trajectories are fed to the meta learner. It takes like a bunch of trajectories from the base learner interacting with each environment. It will generate an embedding that represents this environment. And to do that, we leverage a bidirectional RNN to generate this embedding, give it the input, encoding the behavior of the IO agent in managing the workloads, because the trajectories include the states, action, and the rewards at each time step. And the embedding is then fed back to the base learner as the state input to generate the action. So what is this embedding? Like, how do we interpret this? So from the system's perspective, the embedding encodes both spatial and temporal characteristics of the application workloads. Why is that? This is because for different applications, the same scaling action of the resources might lead to different states. For example, it could be like different latency changes or resource utilization changes. And these are included in the trajectories as either like states, actions, and rewards. And for example, it can be shown in this like left-hand side. We have the performance heat map. Basically, it shows the performance sensitivity to resources. And the darker color means that we have worse performance given the resource configuration. So in the projected vector space on the right-hand side, basically each embedding from an environment is a dot. And applications with similar characteristics are mapped to or projected to adjacent locations, while like applications with quite different characteristics are projected to locations that are farther away from each other. And this is also true for temporal characteristics, because the trajectories is also like a time series. And it is like, it contains time-stepped like state or like rewards. Basically means that what's the performance right now, what's the utilization right now. And this indicates like the load patterns, load arrival patterns or utilization traces. And likewise, applications with similar loads, like load variation patterns, are projected to adjacent locations. And then in the evaluation, we are interested in three main questions. First, does Aware provide fast model adaptation to new workloads, essentially to understand the value of meta-learning? And the second, how does Aware perform in online policy serving during workload changes? For example, it could be the table I listed, like the file size changes, image dimension changes, or the ML model changes. And third, how does Aware perform in the early stage of policy training compared to no bootstrapping? And for the experimental setup, for workload generation, we adopted 16 representative serverless function segments, as serverless workloads typically require dynamic autoscaling. And then we generated 1,000 synthetic applications by randomly selecting and combining these segments from the pool. And for IO agent implementation, we adopt the IO agent from Firm, which uses DDPJ, an actual critique IO algorithm. The reward function basically consists of 2 parts. It gives higher reward to higher resource utilization, and in the second part, it gives higher reward to the higher SLO preservation ratios. And then we training or retraining the IO model for new application workloads. We found that Aware adopts 5.5 times faster than transfer learning with model parameter sharing. And it is like 4.6 times faster than transfer learning with additional attributes. And these additional attributes includes, for example, the map of performance sensitivity to resource allocation changes. We do this like by profiling, like manually profiling this, and then look at this map, and then encode this map as vector input to the IO agent. And during retraining, Aware saves up to 72% CPU cycles. And because of the faster convergence, it also reduced the CPU and memory utilization deficit by 4 times and 6 times. And it reduced the number of SLO violations by 7 times. In the evaluation of bootstrapping, Aware had 47% and 32% higher CPU and memory utilization. It reduced SLO violations by 16.9 times compared to Firm without bootstrapping. And then in the evaluation of online policy serving performance, Aware had a 9% and a 14% higher CPU and memory utilization. And then it reduced the SLO violation by 3 times compared to firm without retraining, monitoring, and triggering. And in conclusion, we have proposed Aware, which is an extensible framework for deploying and managing I/O-based controllers in production systems. Aware basically tackles 3 challenges with 3 key components. It provides fast adaptation with meta-learning and reliable I/O exploration with bootstrapping, combining the offline training and online training. And it provides robust online performance, like stable online policy serving performance with timely retraining and continuous monitoring. We have demonstrated Aware in the case of workload autoscaling. And this evaluation results shows that it adapts the learned policy to new workloads by 5.5 times faster than the existing transfer learning-based approach. It also provides stable online policy serving performance with less than 3.6% reward degradation. It achieves 47% and 32% higher CPU and memory utilization, while reducing the SLO violations compared to online policy training, initial policy training without bootstrapping. However, on the limitation side, meta-learning does not guarantee adaptation in auto-distribution cases, which might be mitigated with detection and fine-grained customization. But this might happen rarely in cloud data centers, as the training data might already include diverse application sets. And in the future, we are looking at to extend this meta-learning-based framework, which basically learns to generate embedding that can represent the workloads for other workload-aware machine learning for systems cases as a general paradigm which facilitates fast model adaptation, which could be scheduling or power management, et cetera. And that would be all I have today. And I'd like to thank all my collaborators, and I'm happy to take any questions. Thank you.